Hey, AP Chemisters, this is Mrs. Vandelay bringing you Blankwalle Chapter 12. So, Chapter 12 is all about solutions, and we go into a lot more detail than you would have had already in your first year chemistry class and what we've already done so far. We will revisit the idea of molarity again, don't you worry, it comes back, but there's a whole lot more to it, okay? So, Section 12.2 is types of solutions and solubility. A solution should be a review, is defined as a homogeneous mixture. What does that mean? Same throughout. Of two or more substances in a single phase. That's what we mean by same throughout. It does not have to involve liquids, although we most commonly think of that as they are. Air is a solution of nitrogen, oxygen, carbon dioxide, etc. Believe it or not, solder, if you ever heard of that, is a solution of lead and tin. So it does not have to be just liquids, okay? A solute is the component in the lesser concentration. It's the dissolvee, if you will. The solvent is the component in greater concentration. It's called the dissolver. So here's my picture over here. This is obviously like an ocean wave. So ocean is salt water. So if you look, you'll see the green and the purples. Those are your sodium ions and your chloride ions, and they are being dissolved by the water. Obviously, the water is in greater concentration than the salt ions are, okay? And so here's something else you should have already heard about from your first year chemistry class. It's called the effect of intermolecular forces. Like dissolves like. So polar molecules and ionic compounds tend to dissolve in polar solvents. All right, just think of ionic compounds as an extreme case of polarity. We've already learned about, we have London dispersions, we have dipole-dipole, we have polar or hydrogen bonding, and we have that ion dipole attractions, okay? So that's where the ionic compounds come in. And here was a joke, so I thought you'd like to know the jokes, all right? So a bunch of bears jumped into a river and one dissolved completely. It was polar. Thought you'd like to know. That's a joke, okay? All right, so again, I just listed, these are the four types that we're looking at as far as polar molecules dissolving what? Polar molecules dissolve interactions of dipole-dipole, hydrogen bonding, and ion dipole, okay? So what about nonpolar? They're going to dissolve in nonpolar because the only thing going on there is the London dispersions, okay? So interactions. So problem number one, what must occur for a solution to form? Well, let me set this up. Let's look over here in this beaker, all right? Three things have to occur, okay? And it's all really, this is my microscopic version, all right? So I'm looking at my microscope and seeing what's going on. Well, what's happening here? We have solvent interactions. How much those water molecules like each other? We have solute interactions. How much do my solutes, how much does sodium chloride like each other? And then we have the attractions of the solvent and the solute, all right? And what happens here, what we are setting up, if you will, is the idea of when do things dissolve and when don't they? When are things exothermic and when are things endothermic? We're kind of getting that all set up, just like that hand warmer lab we did. So let's talk about the solvent first, all right? What do I have to do first? I have to separate the solvent and the solvents, all right? And I need to spread those water molecules apart to a degree so that the ions or the other polar molecule, the solute, can fit in that space, okay? So I need to create space in the solvents, between the solvents, okay? What else do I need to do? I need to separate out the ionic or the other polar solute, okay? So obviously, if like dissolves like, so if we're talking about water and something else, it's polar or ionic. And so therefore, there is some attractions between the solutes that keep them together, so you have to break those apart, okay? And then what happens, a solvent, hang on here, solute, all right, when they snap together, all right, when they come together, actually energy is being released when they come together. So this phase right here, all right, is going to be endothermic. Okay, so I'll do that. That's this part right here. The solute is also endothermic, but then the energy when the solute and the solvent come together, that is your exothermic energy, is released. Okay, so what happens? A solution always forms if the solvent-solute interactions are stronger than the solute-solute. So in other words, if the solute particles like each other so much, they don't want to spread out, or they don't want to separate, they don't want to be attracted to the solvent, it's going to be considered insoluble. All right, but if the solvent attraction is great enough to the solute, it will. So I want to read to you a passage from your book, all right? I think this explains it very, very well. So if you don't have your book handy, I'm going to read it to you anyway, okay? So this is what it says. It says, if solvent-solute interactions are weaker than the solvent-solvent and solute-solute interactions, in other words, if the solvent molecules and the solute molecules each interact more strongly with molecules of their own kind than with the molecules of the other kind, then a solution may still form, depending on the relative disparities between the interactions. If this disparity is small, the tendency to mix results in the formation of a solution, even though the process is energetically uphill. If the disparity is large, however, a solution does not form. For example, consider mixing hexane and water. The water molecules have strong hydrogen attractions to each other, but cannot form hydrogen bonds with hexane. The energy required to pull the water molecules away from one another is so great, and too little energy is returned when the water molecules interact with the hexane molecules. As a result, the solution does not form when hexane and water are mixed. Although the tendency to mix is strong, it cannot overcome the large energy disparity between the powerful solvent-solvent interactions and the weak solvent-solute interactions. In general, we can use the rule of thumb that like dissolves like when predicting the formations of solutions. Polar solvents, such as water, tend to dissolve many polar or ionic solutes, and nonpolar solvents, such as hexane, tend to dissolve many nonpolar solutes. Similar kinds of solvents dissolve similar kinds of solutes. Okay, so that kind of explains, all right, what's going on here. So the energy needed to separate them is so great, and this is an uphill battle, it's not going to happen, all right? But if you do get more energy out of this attraction, if you will, then it will happen. And again, this is all due to, or the result, I should say, the consequence is, again, like dissolves like. Nonpolar dissolves nonpolar, polar dissolves polar or ionic. Okay, so hopefully that helps. If not, go back in your book and reread it again. Okay, I'll only read it once for you. All right, so problem number 2 says vitamins are classified as water-soluble or fat-soluble. Water-soluble vitamins dissolve in bodily fluids and are easily eliminated in the tinkle-winkle, so there's little danger of overconsumption. Fat-soluble vitamins can accumulate in the body's fatty deposits. Overconsumption of fat-soluble vitamins can be dangerous to your health. Examine the structures of each vitamin shown and classify it as fat-soluble or water-soluble. I think we've already done this as a homework problem from chapter 11, but hey, let's review it anyway. So take a few minutes out and decide which is which, okay? So pause this, answer the question, come back when you're done. All right, how'd you do? Well, vitamin C, well, look at all these oxygens all over the place. Because of all those oxygens, it is a polar molecule, therefore it is water soluble. Vitamin K over here is only 2 oxygens, and look where they are. They're in opposite ends. So what happens to those dipole moments? In a sense, they cancel each other out. So vitamin K3 is considered a nonpolar, which is a fat soluble, okay? Then here we have vitamin A. If you look at it, it's all C's and H's except one little OH over here. So the entire molecule is pretty much considered nonpolar. It is fat soluble. That little OH is not going to make the whole molecule polar. Sorry about that. If it was a smaller molecule, yes. But there is a point when it's so large with all those nonpolar C's and H's, it doesn't count. Then there's vitamin B5. What am I looking at? I see a couple of O's over here. I see an N. I see some more O's. All right, there's enough O's and N's spread throughout. This entire molecule is water soluble. How'd you do? All right, so let's look at problem number 3. So which solvent, water, hexane, would you choose to dissolve each of the following? Well, before you answer that, what do you know about water and hexane? Well, I sure hope by now you all know that water is polar. I sure hope you knew that. And hexane is nonpolar. What is hexane? C6H14. Just C's and H's, no big 4 in there, okay? So that should help you then decide A, B, C, D. And why don't you take a minute out and answer these questions, and when you're done, we'll come back and look them over. Okie dokies, how'd you do? Well, NaCl is ionic, and we know from experience it does dissolve in water. Not a whole lot, but it does, all right. HF, oh my goodness, look at the hydrogen bonding, highly attracted, okay. What about CH18? That's octane, okay? That's what you put in your gas tank, all right? Polar or nonpolar? Hope you said it was nonpolar, therefore hexane would be a good choice. And then the next one, I hope you know, is ionic, and therefore it is water soluble. And if you remember your solubility rules, all ammonium compounds, all sodium compounds, all potassium compounds are soluble in water. So you know you have enough attractions to pull those away than, you know, not, let's put it that way. So it's not the exception to the rule. It's definitely going to happen, all right? Let's look at problem number 14, or number 4, excuse me. All right, so decide whether the liquid hexane or liquid methanol is more appropriate solvent for the substances grease and potassium iodide. Well, what's liquid hexane, polar or nonpolar? Well, I think if you recall from our discussions in the previous problem, hexane is nonpolar. What about methanol? What does methanol end in all? So it's an alcohol group, which is an OH group, hydrogen bonding. Therefore, it's extremely polar, isn't it? Okay, so once again, what's going to dissolve what? So what's going to dissolve grease? What's going to dissolve Ki? Figure it out. All right, well, hopefully you came up with liquid hexane here and liquid methanol here. How did I know? I don't know what grease is. I didn't show you the formula for grease, but does grease dissolve in water? The answer is no. So if grease does not dissolve in water and water is polar, therefore grease must be nonpolar. So you need to have that nonpolar solvent in this case. Ki is ionic. It's a potassium, so it will definitely dissolve in a polar solvent. I think that's it for section 12.2. Don't wait to be great. We'll see you in a little bit.